All right, ladies and gentlemen. So I know we've been talking about acids and bases in classes, and I've been saying acid is an H plus donor and base gives off an OH minus, but I want to show you something. All right, so here I have some sodium carbonate, which has the formula Na2CO3, so it doesn't have any H plus to give, nor does it have an OH minus to give. I got some water right here, and I got some phenolphthalein, which you guys should be familiar with. You know, it's acid-base indicator, and you can see when I put it into the water is clear because the water is neutral, and phenolphthalein is colorless in a neutral solution. But let's see what happens when I take some of this sodium carbonate, just a little bit, and I put it into the water and phenolphthalein mixture. All right. Oh man, look at that. HUD turns pink right away. Why? Why? That is my question to you guys. That is a super basic solution. Where'd the OH come from? You know, how did Na2CO3 give off an OH? Give you a hint? It didn't. So in class we've been talking about acids and bases in one specific way, that an acid gives off an H plus and that a base gives off an OH minus. But there are other ways to define what an acid and what a base is. The one definition we're going to look at is the bronsted-lowry acid-base definition. We want to be able to identify acids and bases based on the bronsted-lowry definition. All right, so if we go back to what was earlier in the video, I added some sodium carbonate, shown over here, Na2CO3, into water. And what happens is, well, it's an ionic compound, so the sodium ions and the carbonate ions are going to separate from each other. And basically, what we're interested in is the H2O and the CO3 minus 2. So what happens is hydrogen is kind of dangling off the water over here, and it's only got these two shared electrons in between it and the oxygen. And then there's a bunch of unshared electrons over on this oxygen. And that is going to bond with the hydrogen. So what's going to happen is we're going to break this bond here, and that hydrogen is going to move over to the CO3 minus 2, just like that. So what happened was the CO3 minus 2 took that hydrogen. So now instead of having a minus 2 charge, it took an H plus. So now it is only minus 1. The H2O was neutral, but it lost an H plus, so it becomes negative now. Now, hopefully, you recognize what this ion is. If it's an OH minus, you know, that is familiar. That's a hydroxide ion, which is what we've been saying makes a base a base. It gives off an OH minus. So in this case, it wasn't that the salt gave off an OH minus. It was that it reacted with the water and produced an OH minus. So ammonia does the same thing. Ammonia is, NH3. It's got an H down here and a lone pair of electrons over here that are able to react with an H that's in the water. So the water breaks the bond here, and that hydrogen's free to go hang out with the NH3. So if we look at our products, well, NH3 is now NH4 because it gained an H plus, and it's also got a positive charge because it was neutral and it gained an H plus. And water lost an H plus, so it's become an OH minus. All right, so hydroxide, our previous definition, we were talking about how a base is something that gives off an OH minus, like sodium hydroxide. Yeah, it gives off an OH minus. And why is that basic? Well, an OH minus is produced, and that OH minus can also react with the water that's in there and say, hey, well, this OH, there's really a bunch of electrons around that oxygen, which are going to attract one of these hydrogens to it. And we can break this bond, and we can make H2O here. And now we're left with OH minus over here. So it's still really the same thing. It's taking an H plus from something else. And that's what makes it a base. So we need a new way to define these things because there's, things that don't have OH minus that act like a base. So we need a different way to define what a base is. We used to say, the Uranus acid, it gives off an H plus, and the base gives off an OH minus. The new way that we're going to look at things is bronsted-Lowry acid is a proton donor. Now I want you to take a look at something real quick. Let's think about hydrogen. Hydrogen has atomic number 1 and a mass of 1. So it's really just one proton surrounded by an electron that's going around it, right? How do I become H plus? All right, well, if it's positive, it must have lost
an electron. So let me get rid of that electron over here right now. And what are we left with? It's just a proton. So really, a proton is an H plus ion. They're the same thing. So when we say, by this definition that it's a proton donor, we're really saying the same thing. We're just using different words to say it. We're being more general. We're saying H plus. We're just going to call it a proton. And now the new way to define a base would be that the base is a proton acceptor. All right, it doesn't have to be OH. OH will accept, if I had an OH minus and an H plus, the H plus would, be donated to the OH minus and give us H2O. That would still work. But there are other things, just like in the example with NH3, that can accept a proton. So we got H2O here, right? And it goes, hey, the water can actually donate a proton to the NH3. So that we end up with NH4 plus and OH minus. So in this case, the NH3 would be the base because it accepts a proton, and the H2O would be an acid because it's donating. So here's a couple more examples to help show you what I'm talking about. So here we got HCl, which we know from the Arrhenius definition to be an acid, and H2O is going to be the base. So if you see what happens, well, I have HCl, and what do I end up with? I end up with H3O plus and Cl minus. All right, well, how did that happen? Well, this hydrogen had to have been donated to the water, the H2O. All right, well, if it's donating an acid, right, acids donate, the base accepts. All right, so HCl would be the acid, H2O would be the base. And if we look at the reverse reaction, well, let's think about this. What's happening? I go from H3O plus to Cl or to H2O and Cl minus to HCl. So the reverse reaction is taking one of those and giving it to a chloride ion to give us HCl. So we have special words for these. So H2O would be the base, and the H3O would be the conjugate acid, and Cl minus would be the conjugate base. So you can see that they're paired up. The acid is HCl and its conjugate base is the Cl minus. It's the thing without the proton. H2O is the base, the conjugate acid is the thing with the proton. All right, so if we take a look at NH3 again, all right, well, I start with NH3 and I end up with NH4. All right, well, it must have gained a proton. I start with H2O and I end up as OH minus. It must have lost one. So it took one of these H's and gave it to the NH3. Well, that makes it the acid because it donated, and NH3 would be the base because it accepted. Now, if we look at the reverse reaction, we got start with NH4. Well, it ends up as NH3, so it must have took one of those H's and gave it to the OH minus, which means that this is the conjugate acid, and OH minus is the conjugate base. All right, one more example. So HC2H3O, then H2O gives me H3O plus and C2H3O2 minus. Interesting. So what happened? Well, I know H2O got an extra proton, so I know it must have been the base. Where did that extra proton come from? The acetic acid over here gave it to the H2O. All right, well then, since it donated that proton, it's the acid, H2O is the base. H3O plus, if we're looking backwards, would be the conjugate acid. And C2H3O2 would be the conjugate base. So if I had to summarize, basically, the Arrhenius definition is you have H plus and you have OH minus, and it's very specific, right? It's saying it's specifically these things. Now the Bronsted-Lowry definition is a little more general. It's saying, a proton donor and a proton acceptor. It doesn't have to be OH minus. It can be anything that accepts the proton, right? So acids donate, bases accept. I remember the stupid little trick, ABBA. It makes me think of ABBA, but it's different. The musical group, Dancing Queen, right? But instead of ABBA, it's ADBA. And that's just a stupid trick that works for me. If you can think of a silly trick that works for you, share it with everybody, because maybe it'll work for them too. You guys may or may not know who ABBA is, but I'll rock out to some ABBA. All right, so if you have any questions, bring them up in class. I'll see you there.